Welcome. I'm Hans Christian. This is my colleague Marius. This talk is going to be about our experience using the Multipass feature in Vulkan, which is a very unique feature in Vulkan, not found in any other API. And we're going to go through how we use this feature for our deferred rendering pipeline. So the content of this talk is, first I'm going to explain what Multipass is, how it benefits the driver, and also what it enables a developer to do compared to other APIs. I'm also going to go into some memory management things. Vulkan has a unique transient images and lazily allocated memory, which is quite interesting, especially for mobile. And then we're going to go into some particular case studies where we look at actual real-world performance improvements that can be had by using Multipass over a classic deferred rendering pipeline. So first, what Multipass is that in Vulkan you have the concept of a render pass. You need to explicitly say up front you're beginning a render pass and you're ending a render pass. But there is a feature in Vulkan which allows you to split this up even more. It is possible to say you're starting a render pass, but we're going to have multiple sub-stages in this render pass. And one way you can think of this is, for example, in classic deferred rendering, you can have a gbuffer pass, which is one subpass, and you have the lighting stage, which is the second subpass. While you could do this in two render passes just fine, you can also specify a very specific dependency between the gbuffer stage and the lighting stage. And it's this particular point that allows mobile tilers to really benefit from this new API. So to summarize the classic deferred shading, you have a lot of textures. You will render to, let's say, 4 textures or something like that. You go into a lighting stage where you're rendering to the light accumulation buffer and you're reading a lot of textures as inputs. And that's fine. That's how things have been done for 10 years, at least. But the interesting point is that when you're doing the lighting, you're only going to read the gbuffer at GL frag chord. Basically, the same pixel you wrote in a gbuffer is the same pixel that will enter the lighting stage. And it's this particular case that allows Vulkan Multipass to optimize deferred shading, because you have to express some kind of dependency between the subpasses. You have to say, okay, we have the color and the depth goes in after the gbuffer stage. It has to be flushed out. Then we invalidate some caches in the lighting pass. That's fine. But we can also say this dependency is by region, which means that we only observe the dependency for a particular pixel. The same pixel that goes in is the same pixel that goes out. And if we know this, tile-based GPUs can do a great job here. So to summarize tile-based GPUs, in case you've not really worked with mobile GPUs before, the main idea is that rendering is split up into 2 stages. We have to batch all the geometry up front, and we do all the vertex shading and the binning and tiling up front. Now, after the geometry stage is complete, everything is written out to main memory. And this is essentially a data structure which has assigned primitives to certain parts of the screen. Now, while this is more expensive than on a traditional immediate mode architecture like on desktop, the fragment shading becomes very interesting, because now we can look at a tiny part of the frame buffer and only render that, because we know all the primitives which affect that particular tile. And now everything, blending and rendering and depth buffering, everything happens in local SRAM on the chip, and that's the big key here. Because if we know that we have this per pixel dependency and we have 2 subpasses, and this stuff happens on a tile, we can interleave execution here. So we can say that instead of rendering everything from subpass 0 and then everything from subpass 1, that's the classic approach. What this allows the driver to do is say, okay, we have a tile-based architecture, so we can actually render tile 0 for subpass 0 and go straight to the next subpass, because all the data is available on the tile already. And then we complete everything, flush it out to memory, and then go on to the next tile. So basically, the gbuffer and lighting pass are now merged by the driver into a single pass. And this saves a lot of bandwidth. This is the main win with multipass. Instead of having to allocate up front 4 or 5 extra textures, writing all that bandwidth out to memory and reading all that bandwidth in, we can now just do it on the tile and discard it afterwards. So how do you express this in Vulkan? I mean, surely you can't use texture reads and have it magically be read from the tile. There is a mechanism where you can say that, okay, we have a particular texture that is a subpass input. That's key. So in Vulkan GLSL, there is extra support for this, where you can say up front that instead of sampling a texture at GL frag court, you say subpassLoad. And then it's up to the driver to see, okay, is this on the tile? Is this a texture? And then it can translate it appropriately. And all of this information is known statically up front, because when you do create pipelines, you give it the render pass, the render pass structure. You also give it the subpass index. So the driver knows everything about where this texture actually needs to be loaded from. And there's no last minute shader patching or anything like that. That would have to be the case on, let's say, GLES, which is always nice. So on an immediate mode architecture, it will probably always just be read from a texture, no big difference from what tilers could do. But we would select either something like a texel fetch if the texture is not on the tile for some reason, or if it is, we can just redirect it to some magical instruction that reads from the tile buffer. So we have removed the bandwidth, but what about the memory storage? Because storing a big G buffer at, let's say, 1440p or even 4K takes a lot of memory, hundreds of megabytes. And we would like to avoid even allocating that memory. And Vulkan has support for saying that an image is transient, where you say, okay, this image, I don't expect to use it outside a render pass. It's just there to magically store some temporary buffer. And on tilers, you could then expose a lazily allocated memory type, which is a separate memory type, at least for us, where the texture is not backed by physical memory at all. You only give it virtual address space just in case, but it will not be backed by physical memory if you allocate, which is great. Virtual address space is almost inexhaustible, at least on 64-bit, but not having to back the G buffer by physical memory is very nice. So the summary for Multipass is that it benefits everyone now, because unlike before, we did have these weird magical extensions on GLES, for example. You could access these kinds of things, but you would need very specific, special rendering paths to be able to take advantage of this. But now everything is under the same API. The same API code will run just as efficiently on mobile and desktop with the same API, which is really exciting, because now this is much more accessible to developers. And by expressing your intent like this, you're giving all drivers the opportunity to optimize for these kinds of scenarios. So instead of writing 2 separate render passes, merging it, you give the drivers some opportunity to do a better job, especially on tilers. So now moving on to some test cases. So we start off with probably the simplest case there is. This is a screenshot from our Vulkan SDK multipass sample, which is a bare minimum sample for how to write a multipass render pass. So as you can tell, the scene is very simple. There's a few lights here, which causes the different colors. And this is used as a baseline. And we want to test what's the difference between using a classic deferred rendering where we have 2 render passes with textures, or if we use the multipass feature. So what we want to benchmark here is overall performance, of course. Ideally, we would like to see some improved real FPS, which is always nice. But the main thing we want to focus on is improved bandwidth, because bandwidth translates very directly to power and battery life on mobile, and we really want to reduce bandwidth. That's the main motivation. If we get improved performance, that's a boost, but that's not the main thing we're looking for. Here's the G-buffer. It's a reduced G-buffer. There's no PBR materials like specular and roughness, that kind of thing. It's just plain normal and albedo. So I measured this on the Galaxy S7. We took the numbers before the S8 was out, so S7 it is. I had to bump the resolution up to 4K because it would hit V-blank or 60 FPS V-sync. Without it, the scene is just too simple. But interestingly enough, in this sort of best case scenario, we did actually get a 30% FPS improvement, just because writing out all this bandwidth becomes a real issue for performance. It's just too much bandwidth. But the bandwidth in the multipass version was reduced by 80%. Consider a case where you have a classic G-buffer thing. You're writing out 4 textures or 3 textures, and you're reading back 3 or 4 textures, full resolution, and then you're writing out the final color. So that's like 9 full frame buffers written out to memory. But in this case, the G-buffer is discarded. It's not written out. It lives only on the tile. Depth only lives on the tile, although in most cases you would need for post, but that's just one texture. And then the color. So in theory, it's 80–85% bandwidth reduction is certainly possible for these kinds of things. And in this case, it translates to real performance benefits. And I'm sure that this would translate to much better sustained performance as well, just due to the fact it uses much less power, although we didn't measure that specifically. So, of course, this is just a trivial scene, and no game will ship something like this. So we wanted to take a step further and test something more realistic. And the go-to scene is the Sponza scene, with a lot of lights and a lot of fancy shading to sort of simulate a high-end mobile game. 610 spotlights scattered around with full PBR, full HDR, reflection probes, shadows, tone mapping, bloom, all these kinds of things to sort of simulate something realistic, essentially. So we start off with something like this, just plain Sponza with some lights. We add a bunch of spotlights, and to make it even more interesting, some projected textures on top of that. That's basically the whole scene, and in actual reality they're spinning around to make it even more fun. But so this is the kind of overdraw you will see. This is using the classic blend light volumes on top of the light buffer, which is kind of going out of fashion on desktop just due to the fact that bandwidth is a real issue. But for us, this is blending on tile, so it's not really a performance issue. We haven't tested clustered for or cluster deferred, but that would be interesting, of course. But this is the kind of overdraw we're seeing. Fairly significant, but not completely artificial either. So we tried a bit to reduce the overdraw. There is the classic stencil culling technique, which is, no one is really using that anymore, but it was popular many, many years ago. The idea is that you update stencil state, you render the back faces, flip it, render the front faces, and so on. Of course, you could do that. You could do this now, but it's still a bad idea, just to the fact that it doesn't scale at all. I mean, you have to render 2 draw calls per light, and if you scale it up to 1,000 lights, that's not, I mean, no one is going to spend 2,000 draw calls rendering light volumes. So we wanted to try something that gets most of the benefit from stencil culling without using so many draw calls. So we tried a clustering scheme where we cluster lights along the z-axis and sort of render them to get sort of a conservative backface culling approach. And essentially, we would create a 2-bit depth buffer in stencil. Stencil is also going out of fashion, but there is 8 bits you can use for something, right? So why not use them? So this is what the stencil buffer looks like before entering the lighting stage, where you have sort of peeled out the stencil buffer in fixed function. So the color shades further into the scene is basically the different depth layers we have. And that's used as a second depth buffer when we're rendering the lights. So the performance there was still a pretty good win. It's still 1440p is a bit too much, obviously, for mobile, so don't expect 60 FPS there. This was more like 1520, but it's still pretty good considering how much processing it does. The bandwidth reduction now is 50 to 60% instead of 80, and the reason for that is because obviously it's doing a lot more stuff. It's rendering shadow maps, it's rendering tone map in bloom, it's doing some post, it's doing more geometry, so there's more geometry bandwidth and that kind of stuff. But still, there is an 18% FPS increase in this case, which was really nice. So it is still a win. And now Marius will talk about an even heavier scene.
Thank you. Yeah, so Lofoten was sort of the Vulkan tech demo that we created when launching Vulkan last year. So this is, yeah, a very crazy type of scene with 2.5 million primitives. It's not what you would typically use for mobile. So we had to do a lot of trickery in order to make it run. Initially, it ran at like 1 to 2 frames per second, and we went out of memory a couple of times. But we got it running quite nicely. So yeah, we had to implement things like software occlusion culling, things like that. We still ended up with 500,000 primitives per frame, but that was sort of within the budget. So the rendering itself is very similar to the Sponza test, but we also have reflection probes and lots of environment effects, as well as ocean FFT simulation with separate reflection and reflection passes for the ocean, together with HDR and bloom. Yeah, so even with all the bells and whistles, the main chunk of work is still the G-buffer pass and the lighting pass. So this is the typical flow in the rendering of the scene. Yeah, so as Christian mentioned earlier, only the actual lighting pass is backed by physical memory. And since rendering to tile is so cheap, we simplify a lot of the hackery that deferred renderers might have to do to deal with emissive forward-like materials. So this was used especially for things like ocean rendering to propagate refraction and reflection correctly. Also light surfaces and stuff like that were also stored simply as emissive directly into the lighting buffer directly. Yeah, and the lighting pass simply just blends additively the lighting into the light buffer. So basically on top of whatever emissive data that you had already written to that. And the final thing is like a full screen pass where you apply fog to this. Yeah. So yeah, fill rate doesn't really cost bandwidth on in this case. So we can so we basically have the nice benefit of using very small shaders, since this is really good for instruction cache and register pressure, especially on our hardware. The downside is that we have to read the tile memory multiple times and reconstruct world position more. So it's it's a balancing thing. So to make this work in our engine, we decided very early on to make all the rendering very explicit. So we have explicit commands to do begin render pass, next render pass, and end render pass. Doing this, it was also quite easy to backport to OpenGL, because we also still want to support OpenGL for at least for comparison purposes in our engine. To deal with transient images, we essentially added a concept where a render pass would request virtual attachments, and they basically only serve as scratch memory for the gbuffer. And this also made the code simpler, because we didn't have to explicitly juggle textures for all the render targets. This is basically how a typical the code is written. So you have explicit begin render pass, you do your gbuffer, you go on to the next subpass, render all the lights, and you finally end it. So the old style GL wouldn't allow us to do this the same way. So this is the result we got. So this is obviously a lot heavier than Sponza. We tested this on 1440p native resolution on an S7. So we saw a 50% bandwidth saving, about 12% frame rate increase, and we also measured power on this demo. We basically compared multipass with regular forward shading, with regular multiple render target rendering, and we saw a 25% energy saving, which is substantial. Just another screenshot from the demo. So some performance considerations for tilers. So on-chip memory is very limited, which also means that the gbuffer size is limited. Note that, for instance, depth and stencil are stored separately, so that helps a bit. Reducing tile sizes is supported for larger gbuffers. This can give you quite large performance penalties, since you get fewer threads active and worse occupancy per shader core. The GPU also needs to do more scans through the tile lists, which can worsen the performance even more. Supporting multipass across multiple APIs can be difficult, especially if you want to preserve feature parity between the APIs. So we found that having this concept of render passes at a higher level in the engine was a must-have, since it was quite easy to make this also work in things like GL. So for things like subpassLoad, which is basically only available in Vulkan GLSL, we emulated this in other APIs by just injecting a stencil fetch. We also have a code path for remapping subpassLoad into pixel local storage variables. Yeah, and finally some tips about handling image layouts. gbuffer images are by design only used temporarily, and since the application should not have direct access to these images, we don't really need to track these layouts. So just use external subpass dependencies for transitioning. Yeah, that was all we had. Do we have any questions?
Hi. How does this work with multi-sampling? I mean, is it sharing the buffer with the multi-sampling, or the tile gets smaller? Have you tested?
So you mean like subpassLoad from a multi-sampled attachment?
Yes.
I haven't tested that particular, but it should work in API. There is a subpass input multi-sampled, and then you can read a particular sample.
Yeah.
So that you should be able to do this kind of thing with multi-sampling as well, but I'm not sure how efficient it would be.
Does the tile buffer available for the multipass become smaller if you're using multi-sampling?
Yeah, so if you have a G buffer, that's 128-bit, and then you want to multi-sample that, then the tile will have to become very small.
Yeah.
So what I'm interested in with display list-based rendering to tiles is what happens if the display list gets full and you run out of memory. How does the GPU behave then?
When that happened for us, we just, missing geometry basically, but we didn't really see didn't get any errors at least.
Do you have a sort of rough idea how big the display list becomes with a mobile GPU?
So you're talking about the geometry now. All right. Yeah, you have to. It has to be basically artificial. You can't push it to. There is a certain size until it starts to go out of memory, but it's so huge that it needs to be artificial. Many million primitives at least.
Yeah.
I think it will be reported. I'm pretty sure I've seen it. If it fails, it will give you a device lost eventually. Something like that. Yeah, please don't do that.
So, as one of the other mobile vendors in the room, where am I? Here, hello. Hi. As one of the other mobile vendors in the room, I would say that as far as we can tell, at least 3 vendors that definitely do this sort of thing have wildly different answers for the size question. I think it's probably safe to say that if the amount of memory takes more, it should never take more than the amount of memory it would cost for the render buffer. But I suspect all the different vendors have different strategies for that, and you're better off asking that pointedly if you need to know the answer. We did consider actually adding something like a query to Vulkan, but we just couldn't agree on semantics because it was so different. So.
Thank you. So I remember asking this kind of question, or talking about this kind of functionality before, and somebody in the audience was asking if there is the ability to combine subpasses and access them one tile at a time, but when you've run out of space, you then spill and end up writing to memory more in the way that an immediate renderer would. If that's a fallback path that everybody's implementing, the question that I was asked was, how do you know when it's going to happen? And can your application do anything to detect which path you've gone down?
Right, so yeah, knowing exactly what the driver will do, this is generally a little bit of problem with the multipass interface. Many will argue it's a bit too opaque. So ideally, we would have some kind of way to query exactly what the driver is doing, just because there are trade-offs there, right? I mean, you can, do we want a smaller tile and have more space? Do we want to spill a little bit to memory? Let's say an L1 cache or something like that. Yeah, I don't think there's a good solution right now. I mean, we did release best practices document recently with a lot of details. It's not, of course, enough detail that you can say exactly what the driver will do. We are working on a way to. We are working on a Vulkan layer that can, ideally, should be able to track these kinds of things. But yeah.
So, do you have any more info on the cluster stencil light culling, or was there a presentation on this? Some
There's no particular presentation on it. This was a random 2-day hack. I can explain you more in detail if you come talk to me afterwards.
Right. Okay. And the other question is that you had those slides with the performance graphs. Can you explain what the colors mean?
You mean the streamline graphs? So.
What tool is that?
Right, so the measurements here are, I'm not sure if you can see the numbers, but there is the GPU cycles overall. So this is for one frame each. So the multipass here is 72 milliseconds, the MRT is 81. And that's sort of the number of GPU cycles it spent for that frame. So the top will be the total GPU. There is JS0, which is how much fragment processing was active. There is how much vertex was active. And then there is the bandwidth in bytes. And MRT, the total GPU bandwidth is in total 230 megabytes, which is quite a lot. For multipass, it was 110-ish, something like that, so roughly 50% save. And in the 12% FPS increase is the difference in GPU cycles, 52.3 million cycles versus 46.6. And JS0 and JS1 does not necessarily add up to GPU cycles because there is overlap in the processing.
What if you are heavy ALU bound, if you are not having many texture reads, do you have any measures for this scenario?
Yeah, so this is from Streamline, and you can get a lot of counters. This is just 3 counters, basically. But you can get like how many arithmetic instructions, how many cycles were spent there. You can have load store, texture cycles, issues. You should just check out DS5 Streamline. It has all of these kinds of counters. You can easily see if you're arithmetic, texture, or load store bound.
No, I'm asking the light of the...
All right. Okay, so
light of the measurement
in this
of this,
particular, so in this particular, we are slightly arithmetic bound. Load store heavy, not much texture. Texture is maybe 20% of arithmetic. It's really arithmetic and load store bound, slightly more arithmetic bound.
Any last